Hello, our presentation is on Approximate, Byzantine fault tolerance and distributed optimization. I am Kyle Zunick, and our team is Prasanna, Rooney, Theo, and Xiaodong. These are the publishers of our paper, along with a screenshot of the paper. In today's agenda, we are going to do a brief paper introduction. We're going to define a few key items. We're going to talk about gradient descent, and then we're going to talk about fault tolerance by gradient filtering using a couple different algorithms, and then we are going to look at the experiment's results, and then we're going to go through a couple closing items. With that being said, Theo is going to start us off.
Thank you, Kyle. My name is Theodore Elmberg. I'm going to go first and introduce what is a distributed optimization system. A distributed system is any system communicating together, or it can even be two people talking and exchanging information. Here we have some example. We have a server-based system where server exchange information with some agent. We call agent any device connected to the network and exchanging data. We have here peer-to-peer agent. We even have a server talking to server, which locally talking to agent. So I'm going to go ahead and provide a definition. A distributed optimization is an important concept with application in a network, data exchange, learning algorithm, or control theory. The distributed system is capable of massive data computing. They then need to rely on consensus for each particular state of data exchange. So every time they exchange data, they have to come to agreement that those data are reliable. A distributed system has to be reliable, consistent, available, repeatable, and reproducible. We can imagine, for example, if you open a web page, you need that web page to be reliable without bringing any viruses, any problem. You need it to be consistent. So it's the same page every time you put that address, is the same page which came. You need it, of course, to be available. You need it to be repeatable. So every time you open, it's the same thing, and you go to the same process, and reproducible, of course, any time of the day or any other person who open it. It has to be the same page. The challenge is now to detect and locate any faulty agent in a distributed system. I'm going to introduce the Byzantine fault tolerance. Thank you.
Hello, this is Kyle Zunick, and I'm going to be talking about the Byzantine general problem. Byzantine fault is a condition mainly in distributed computer systems where some components may fail. The problem is how to know if a system is failing and how to determine what is a good data. A Byzantine fault-tolerant system is when the system is able to function even if some of its components have failed or are reporting incorrect information. These systems are complex to put in reality and are expensive in performance. A reason to use a Byzantine fault-tolerant system is when a system cannot trust anyone on the network and the data needs to be verified. Byzantine fault-tolerant systems are used in the crypto field, aerospace, along with many other fields. So in this scenario, Army A and Army B are trying to communicate with each other. Army A is going to send a command to Army B, and then Army B is going to have to respond to Army A, confirming that they received the response. So Army A sends a attack the city command to Army B, and then when Army B tries to send it back to Army A through a messenger, the messenger is interrupted and the response never gets to Army A. So as you can see, the problem here is there's no good way for a confirmation on either side because it's an endless loop. So let's say then Army A wanted to confirm that Army B, they received Army B's messages. It just keeps going on and on and on. Here is also another example. This is through the general lieutenant analogy, where a group must decide to either attack or retreat. If all groups attack, it will be a success. If all groups retreat, it will also be deemed a success as they're still alive to fight it for another day. The problem scenario is when a few groups go and attack, when the rest retreat. So here in scenario one, we have one general and two lieutenants. The general wants everyone to retreat. The general writes a letter to Lieutenant 1 and tells them to retreat. The messenger sends the letter to Lieutenant 1 successfully. The general writes a letter to Lieutenant 2 and tells them to retreat also. The messenger sends a letter to Lieutenant 2 successfully, but the problem is the messenger accidentally grabbed a letter that said attack instead of retreat. Both lieutenants, to try to verify, ask each other what the general told them to do, and then they store their response. Lieutenant 1 received a retreat command from the general, but an attack command from Lieutenant 2. Lieutenant 2 received an attack command from the general, but a retreat command from Lieutenant 1. Both lieutenants can't make a consensus on what the correct command is and decide to go with what the general told them. This results in Lieutenant 1 retreating and Lieutenant 2 attacking. This does not work as they are not in sync and result in a failure. So to try to solve this problem, we add another lieutenant. So here we have one general and 3 lieutenants. The general wants everyone to retreat. The general writes a letter to Lieutenant 1 and tells them to retreat. The messenger sends a letter to Lieutenant 1 successfully. The general writes a letter to Lieutenant 2 and tells them to retreat. This is also sent successfully. Messenger sends a letter to Lieutenant 3 and tells them to retreat. The messenger sends the letter to Lieutenant 3 successfully, but the problem is the messenger accidentally grabbed a letter that said attack instead of retreat. Now all lieutenants ask each other lieutenants what they received and store their responses. So here, Lieutenant 1 got this, that didn't work. Got this retreat command from the general. And then Lieutenant 1 tells Lieutenant 2 to retreat. And then Lieutenant 1 also tells Lieutenant 3 to retreat. And then Lieutenant 2 tells Lieutenant 1 to retreat. Lieutenant 2 tells Lieutenant 3 to retreat. And now here, Lieutenant 3 has an attack command, which is not the correct command. Lieutenant 3 tells Lieutenant 2 to attack. And Lieutenant 3 tells Lieutenant 1 to attack. So here, we now have all the responses from everyone. Lieutenant 1 says, what should I do? I have a retreat, retreat, attack. So since we have 2 retreats, first one attack, retreat wins. Lieutenant 2 has a retreat, retreat, and attack. Since they also have 2 out of 3, retreat wins. And then Lieutenant 3 has attack, retreat, retreat. They have 2 retreats, 1 attack, retreat wins. So here we see that even though Lieutenant 3 received an attack command, they still went with retreat, and then all 3 lieutenants went with retreat, and this was a successful mission. So for a Byzantine fault-free system, you need 3m plus 1 non-faulty nodes, where m is the faulty node. So basically, less than 1/3 of all nodes can be faulted for successful consensus that can be made. Otherwise, an incorrect decision may be made. So in this scenario, we have 1 faulty node and 2 good nodes, right? So if you have 3 faulty nodes, you need 3 times 3 plus 1, so you need 10 good nodes. If you have 4 faulty nodes, you need 3 times 4 plus 1, or with 13 good nodes. Cost function is used to measure how wrong the model is in finding relation between the input and the output in machine learning. Basically, how badly the model is predicting. The point of a cost function is to judge the performance of the simulation. It is the difference between predicted value and actual value. The cost function is used during the training phase. There are many different types of cost functions, a few are listed here below.
Thank you, Kyle, for your great explanation. It's Theodore here. We're going to go forward and explain the exact fault tolerance. Let's consider this network with 3 agents. Find a fault agent in this network can appear to be a big problem. We're going to divide that big problem into a small problem. So in optimal distributed system, each agent is being assigned by a local cost function when the agent is fault-free. We assume here that agent 3 and 2 are a fault free. So we're going to compute the local cost function Q of each agent I based on a variable. Here we consider the variable being the message exchange. So the global cost function is the aggregation of the local cost function, and we're going to find the minimum of those aggregate local cost functions. But the problem is now the faulty agent can share bias information to prevent the non-faulty agent from making the correct identification. We can imagine a hacker which can hack the computer and make that computer keep providing the minimum local function of that one. So how in that case can we identify the faulty agent? How to achieve a consensus in a distributed optimization system? We introduce the F epsilon resilience, which is a relaxation of the exact fault tolerance. A F epsilon resilience is an algorithm which considers a set of input always provides the same output in all its execution. An algorithm is said to be a F epsilon resilient if its output a point x hat, such as for every subset S of non-faulty agents. So we consider the network with non-faulty agent, and for those non-faulty agent, we always output the distribution of Hixat such as the minimum aggregation of the local cost function is below epsilon, despite the presence of a Byzantine agent. One of the property of the F epsilon resilience is it requires a weaker redundancy condition in comparison to the 2F redundancy. We name them 2F epsilon redundancy. How to achieve the consensus of non-faulty agent? The author explored some deterministic algorithm to achieve that consensus. The author also explored the condition of feasibility and achievability of a desirable accuracy of approximate fault tolerance. The author stated that F epsilon resilience is feasible only if 2F epsilon redundancy property holds true. If 2F epsilon redundancy property holds true, then F to epsilon resilience is achievable. In this presentation, we will discuss the distributed gradient descent method. The distributed gradient descent method is applicable only if the agent costs are differentiable. We can imagine a network as machine learning or regression. This is not applicable for any other kind of network. We will focus on the condition of convergence of such algorithm here. Further, we will introduce the following two algorithms, both derived from the distributed gradient descent. One of them is the comparative gradient elimination, which is a filter, and the second one is a coordinate-wise trimmed means, CWTM, which is also another filter. To finish, we will discuss the comparative result of the two approaches.
Hello all, we will see how the gradient descent will work to overcome the fault tolerance. So it is just an algorithm where the server maintains the estimate of a minimum point and update it iteratively using the gradient sent by its agents. And what that statement tries to say, we will understand more deeply by looking at some diagrams. So right now, just to remember, like basically it is used to minimize the cost function. And as we have seen earlier, what is a cost function? So let's say we have taken the formula of the cost function like mean of g of theta 0 and theta 1. and theta 0 is nothing but the x-axis point and theta 1 is the y-axis points. So we are interested to find a point on this plane or the 2D plane in such a way that our cost function should be minimal. Okay, so now a gradient descent finds the local minimal of a differential function. So how it actually works? So it follows the two steps. So first is like start with some random value of a cost function, or you can take any random iteration estimate and keep changing the theta 0 and the theta 1 values such a way such a way so that you can reach to the local minimum. And if you wanted to compare this with the real time scenario, now let's say you're standing at the edge of a mound. So now say let's say you're standing over here at a point W0, and if you spin around into the 360 degrees, and if you wanted to take a baby step in some direction, and you will go down as quickly as possible to this point. So in what direction you will need to take that baby step so that you will reach to down as early as possible. So technically speaking, you need to reach at the local minimum. So to calculate this, we can follow this type of formula. So let's say we have iterations like t, and this is our current estimate w of t, and which gives the minimum of cost function at each iteration. So now starting with the minimum estimate W0, you can see on this graph, and we compute the gradient of a cost function at W1. And if it is lesser than the W1, then we will just update the current estimate, and because it is moving us to the convergence. So now we keep calculating this cost function with a different estimate, and eventually we will know that we succeeded once we reaches to the bottom of that graph. And this bottom of the graph has shown by these red arrows, you can see over here and over here. So another thing is, as I mentioned earlier, this is an iterative algorithm where the server maintains the estimate of the minimum point. So we have seen what is minimum point, and arbitrary estimate point we have considered initially, and we kept updating these gradients sent by the agents iteratively. So specifically each iteration, let's say we have an iteration from the 0 to n, and the server starts with the estimate of w of t and broadcasts it to the all agents. You can see over here agent 1, agent 2 up to agent n, and the server requests from each agent the gradient of its local cost function at the current estimate w of t. So each non-faulty agent, let's say agent 1, agent 2, we will consider as a agent I, will send back the server the gradient of its local cost function. So these are the gradients of a local cost function respect to these agents. So, and this is denoted by this formula delta of q of I w of t. However, let's say we are considering over here all the agents are non-faulty. These are pure agents. And in case of like Byzantine faulty agents, they may send incorrect vectors as their gradient to the server. Now let's see. So once they send some faulty vectors to the server, then the gradient descent algorithm might go ineffective in presence of the faulty agents. So to overcome this problem, this paper proposes two solutions. One is like coordinate wise trim min and the comparative gradient elimination to handle the scalar gradient. And this part is going to be explained by Rooney.
Hi all, I will be describing gradient filter over here. And basically, a gradient filter is a vector function that is applied to all the coordinates that are all the coordinates, or like we can say that all the estimates that we receive from the agents in the network system, as it was described that the server sends a request to the agents to get the estimates from each of its agents involved in the network. Then the gradient filter is used to mitigate, it is used to resolve the determinant impact of incorrect gradients that is sent by Byzantine faulty agents in the network. It robustifies the traditional gradient descent method against Byzantine fault. So what is like how it robustifies the traditional gradient descent method? I will be explaining in the next slide. So it is like these are the steps that are used in the iteration while we calculate the estimate. The server requests from each agent the gradient of its local cost function and the current estimate if we consider xt, while each non-faulty agent will send the server the gradient that is local cost xt, whereas a faulty agent may send an incorrect arbitrary value of that gradient. Then in the step 2, here is where the gradient filter is applied. Then the server applies a gradient filter that over here we are represented by a grad filter to the end received gradients, and it computes like this, that is the all the vector size are of the same, and it gives us output also of the same vector size. The server then updates its estimate to x, that is t plus 1. This is the step size, that is the increment in it. So in the paper, they have proposed like two gradient filters. That is, the first is the comparative gradient elimination that I will be explaining over here. It is a norm-based gradient filter. It robustifies the distributed static gradient descent method against Byzantine agent. The distributed static gradient descent is in which we usually use determinant value. We get the gradients using derivatives, we can say in like simpler terms. In each iteration, what the server does while applying what is the actual process, like how the comparative gradient elimination is done. Like it applies the server eliminates the received stochastic gradient with the f largest Euclidean norms. That is, you can see over here there are two vectors that are represented by the red color. That is, we are going to eliminate the largest value and the smallest value, and the largest and the smallest vector maybe they may be representing a faulty agent, or they might not be. If they are not representing faulty, but we are sure that the faulty agent's vector value is bounded by the larger non-faulty agent. So we are kind of sure over here that the value is approaching more towards the correct value rather than to the faulty values, rather than to the faulty agents. While in coordinate-wise trimmed mean, in this gradient filter, how it actually applies, how the model is actually applied is like when we receive the gradients from the agents, the server eliminates or it removes the largest and the smallest coordinate, and then it means it. And this is done for each and every coordinates that are involved in parameter estimation. So in the next slide, we can see that after doing it is proven by many of the theorems in the paper, that is the size of the parameter, the size of the parameter d, we can prove that for the comparative gradient elimination, a smaller number f of the Byzantine faulty agent implies the smaller value of d, and therefore better fault tolerance of the algorithm. We can see over here that f is in the numerator. the f of the implies a smaller. Yes, f is in the numerator. That means it is directly related to it. And we can also see that if this is the smaller value, then d also gets like a smaller value. The size of the parameter also gets reduced, and therefore better fault tolerance is achieved. When d is 0, then f is also 0. Then the algorithm intends or it converges to actual minimum point of all the agents, aggregate the cost function in the fault-free case. That is that if f is directly 0, then definitely this will approach to the smallest value. While in that the coordinate wise trimmed mean in this gradient filter, the smaller the value of lambda, that is the closer non-faulty gradients to each other, the smaller is the value of the d, and therefore better is the approximate fault tolerance guaranteed of the grad filter. Unlike the previous grad filter, that is the comparative gradient elimination, we can say that the resilience of this filter is independent of the non-faulty agent, that is f over here. So how the accuracy is achieved under 2f and epsilon resilience. With 2f and epsilon resilience, we can say that the comparative gradient elimination requires that f is less than n upon 3, and the resilience of the coordinate wise trimmed mean is independent of f, that we just saw, that it requires f, and we can say this is achieved only when it is like minimum. We say that it approaches to minimum when f is minimum. So here the condition is like f is less than n upon 3. And with the theorems like 4 and 5 that are represented in the paper, we can see that the resilience of CGE is independent of D, while the resilience of CWT is dependent on D. We can see over here it is dependent on D, while here it is not dependent on D. This means that this is the parameters, the size of the parameters. Here the size of the parameters is not required for us. That is why we say that the resilience is independent of D, and while the resilience of the other, that is the coordinated by stream mean, is dependent on D.
Here we're going to talk about the numerical experiments. In this article, author presents the simulation results of CGE and CW2M gradient filter applied to a problem of distributed linear regression. They assume the total agent number n is 6 and the faulty agent number f is 1. Each agent knows a 2D row vector, which is A, and has a data points can be represented by A, B, and N. B is response and N is noise. And here is how the authors defined A, B, and N. And in this problem, each agent has a quadratic cost function defined as here. So the aggregate cost function of all agents is like this. And we assume in this simulation, agent 1 is to be the Byzantine 40. So, and the 40 agent had two kinds of the behavior. First one is the reverse the true gradients and sending the reversed gradients to the servers. So we call this type is the gradients reverse. And another one is sending random vector to the in the definition domain, and we call this type is random. So notice that because of the filter, the 40 agent will not be used during the simulation. So here we had a set of the non-40 agents, which is H, is from the 2 to the 6. And next we need to obtain the XH, which is the minimum points of the aggregate cost function of non-40 agent sets. And the XH can be solved in this linear equation, and XH is the 1.078 and the 0.9825 is this point. And in this question, the convex compact AW is a 2D hypercube, which means it's just a square, and each edge is from the -1000 to 1000. So it's obviously the x edge is included in the W, so which means the assumption 4 is achieved. And next, the mu and the gamma of the non-40 agent cost function is need to be found. And in here, the mu is equal to 2, and the gamma is equal to the 0.712, which means the gradients of the cost function is a little bit continuous, and the non-Fourier agent cost function is strongly convex, which means the assumption 2 and 3 is satisfied. In app execution, they observe the iterative estimate by the algorithm will particularly converge after 400 iteration. So to measure the approximate faulty tolerance by these two kind of filter, they define the outputs of the algorithm is the x out is after 500 times iterate, which access, and they assume the initial estimate in here, the x0 is like here, is negative 0.0085 and negative 0.5643. And here is the output of the two gradients filter under the different 40 agents behavior. So notice that the distance between the x edge and the x outs is the norm of the 2 points, and also represents the approximate error. And as shown in the in this table, in all execution, the distance between the x edge and the output x out in both cases of the CGE and the CWTM is similar than the Epsilon, which is our approximate error. Is smaller than that. And we also apply the value of the aggregate cost function, which is the loss, and approximate error, which is distance in here. The green line is the filter use the CGE filter, and the yellow line use the CWTM filter. For the blue line, is use the 43 DGD methods, which means the 40 agent will be cancelled out in these methods, and the red line here is the DGD with the Byzantine 40, which means the Byzantine 40 will affect the results. And we can see after iteration 20 times, the results will converge together, which means this algorithm of the two different filters work.
And that concludes our presentation on approximate Byzantine fault tolerance and distributed optimization. Thank you. And our contact information is listed on this slide if there are any questions.